So this is graphics and visualization, E0271. The idea of this first meeting is to answer a few questions about the course. So namely why, what, how, when, and who, right? Uh, so often I like to ask the question why first. Why this course? Or why a course on graphics and visualization? Let's try to answer that in order to set the context. So graphics as a topic or as an area of research um, has a rich history. This goes back to um, the early stages of this goes back to the early stages of computer-aided design. So this is about 50, 60 years ago, maybe also to the origins of computer science. When there was a need to design different objects, and manual design was no longer an option. The reason being that the parts became complex, the designs were could not be in one person's head anymore, and there was not enough space on a sheet of paper to display the entire design. So there was a need to model the 3D world around us. And this application of graphics continues to be one of the major drivers for the field of computer graphics. The automobile industry, among others, has a good need for experts in graphics. So this area is called computer-aided design. And computer-aided design is broad enough that it's not restricted to the automobile industry anymore. It expands out to the architecture industry, VLSI design, and of course, the mechanical industry. What you may be more familiar with is the application of graphics to the entertainment world. This is fairly obvious. It is right there in your face, so difficult to miss. And surely so, this is indeed one of the major drivers for the technology, for the graphics technology. Even if it's not necessarily a big driver for the industry in terms of the number of people involved in graphics, but definitely for driving the technology, this was one of the key reasons. Before computer graphics came into mainstream cinema, it did come out in the form of short films. And one of the major drivers here was Pixar, which is why many of the pictures you see here in my slide are from Pixar's feature films and their shorts. And this continues to be a major driver for the graphics technology in terms of modeling, rendering, and the visual effects. Another major driver for computer graphics is gaming. While this is very familiar to all of you as a user, what you may or may not know is one of the big reasons for computer graphics and the graphics cards becoming a kind of being a consumer product, something that sits on your laptop or on your desktop at less than 10,000 rupees or maybe even 5,000 rupees. One of the reasons for that is the computer games industry. Prior to this, computer graphics was essentially like a supercomputer. It was available only in a select few places. Each machine costed millions of rupees and was available only for some very special purpose tasks. but the gaming industry really drove the need for individual cards, consumer grade cards, and then companies such as NVIDIA and earlier ATI came into the market and really changed the scope and the entire field. Another traditional reason for computer graphics is VR. VR is available to the consumer now, but it has been a very active area for, again, 40, 50 years. And as we will see in the next class, the origins of computer graphics also shares a lot with the origins of VR. So VR, for those of you who haven't seen a formal definition, refers to an immersive experience where you see a 3D world by jumping into the 3D world. Now, you may have experienced this with a pair of goggles, but there are more applications, or one of the first prototypes that used a graphical user interface as opposed to a text interface or a command line interface. And this was also essentially the origin of computer graphics. So this tool called the Sketchpad was developed by by a graphics pioneer, Ivan Sutherland, also called the father of computer graphics. Of course, user interface have evolved significantly. We have natural user interfaces now. We don't need an explicit device in order to control our application. Hand gestures, face gestures, eye gestures are sufficient for interfacing with the different applications. Moving on to the second aspect of this course, visualization. Why visualize? So visualization refers to the visual representations of data. Why do we want to study visualization? Again, there are several applications that drive the area of visualization. Data is something that we are swamped with now. The data comes from different disciplines. Data comes from different devices. We produce data and consume data every second of our lives, essentially now that we are living in a digital world. So in order to understand the need for visualization, let's talk about the different types of visualization and where they are applied. Data that comes from different science and engineering disciplines need to be studied and understood if they have to be used to understand the underlying physical and scientific phenomena. So data visualization plays an important role in almost all science and engineering disciplines, be it on the lower bottom left, the cosmology, or the top left, the medicine, the study of anatomy, or the middle pictures, in biology, the study of virus, or on the right, this is actually a visualization of a fuel in a rocket chamber. So essentially in engineering disciplines. Data comes, like I mentioned, from different disciplines, and it is very critical to be able to visualize data. So here what we see is the visualization of a CT scan of a lung. And what you see in the cyan, the background is blue, where you see the lung. The cyan tries to highlight certain parts of the lung which are abnormal, and the different renderings right at the middle are indicators of potential tumors in the lung. So this data is comes from something called a 4D CT scan, which is essentially a scan of the lung while taken while the lung is functional, right? So that you cannot stop the lung, so you cannot freeze frame and take a snapshot of the lung. The lung is constantly moving. Uh, so the CT scan, the 4D CT scan takes an image of the lung as you are breathing, and then you try to create a static snapshot out of that breathing lung in order to understand the anatomy and to identify tumors if there are any. Visualization plays an important role in biology. This would be a topic of some of the assignments that we will look at in this class, especially the study of molecular structures, as you see on the left, or the study of more cellular structures, how one cell interacts with the other, and so on. Data can be abstract as well. Data can represent relationships. They can represent connections, networks. So the study of such data and their visual display is called information visualization. So there are a huge array of techniques for visualizing such data, so that they are available to the end user who may not understand either the algorithm used for the display or the mathematical abstraction. So these would be users such as social scientists or the general public. Um, uh, so how do you visualize such data, maybe even over the browser, right? So visualizing networks, graphs, visualizing different hierarchical representations, such as the file structures um, uh, in your file system, right? Or uh, voting patterns in the parliament or the Senate, election results, and so on. Right? So this leads to an important area of visualization. So namely the visualization of graph networks, higher dimensional data, where there is no clear representation in the 2D plane or in 3D. Um, uh, so visualization of, for example, neural networks, visualization of data that comes from 10, 20 dimensions, results of your clustering results, and so on. So different reasons for one to study visualization. So next comes the question, what do we mean by graphics? What do we mean by visualization? And here I'm going to try and restrict to the scope of this particular lecture. So, so what is computer graphics? Here's the first answer, which is very, very high level. Graphics is essentially the area where we take photographs using a synthetic camera. So we produce images. So the question we study in graphics is, where does this image come from, right? What is the context? So, and what software, hardware, or algorithm was used to produce it, right? So a quick answer for this specific image. This specific image is an artist's rendition of the sun. So you see some embellishments here. It was created using a software called Maya. Maya, by the way, is built on top of a graphics library called OpenGL. The hardware used for rendering is a regular PC, a desktop, which has a graphics card that supports the rendering of this model. Maya was used for both for modeling and rendering this particular model of the sun. Okay, but that's a very high level answer. So what is really graphics? Graphics is highly interdisciplinary, as we will see in the introductory lectures next week. We borrow ideas from science, mathematics for sure, specifically geometry, algebra, calculus. But we will use ideas from physics, essentially the study of light, color, appearance, material properties, and so on. We will naturally use ideas from engineering, particularly computer engineering, software engineering, the study of software libraries, GUIs. Um, all the rendering is on modern graphics architectures. So this also plays an important role in computer graphics. The data sizes are large, so it's important that the algorithms scale to large data sizes. So scalable systems, multi-core, many-core, and so on also play an important role. There is another aspect of graphics which we may not be able to cover much in this course, namely the interplay using ideas from art. Color and perception is very important in graphics, and a lot of this is studied systematically in art. Illustrative views are very important. Painterly style renderings are quite important. Now, we borrow ideas from art in order to generate such views. So next, what is visualization? So a quick definition would be that visualization is the study of algorithms and techniques, methods for creating visual representations of data. Visual representations are those that could be consumed typically by a human. So this visual representation could be used for either exploring your data and understanding it, or it could be used to communicate what you understand about the data to others, to your peers or to the general public. Now, why visual representation? Why not other representations? Humans are always in the loop when we talk about visualization. And humans are very good at identifying visual patterns, thanks to evolution. Specifically, what are we good at? The human visual system, what is it really good at, right? It is good at a couple of things. So these are natural abilities. One is we are very good at 2D visuals. We have very strong ability to recognize patterns in 2D images. This was true always due to evolution, and more so nowadays because we are living in a visual world where we are constantly looking at images of objects as opposed to only the objects in the 3D world. We also have a very strong ability to integrate multiple images in our brain to form a 3D model. If you think about it, our eye essentially creates images of the 3D world, but we get those images from different viewpoints, and we're able to put them all together to recognize that, for example, a photo of a chair is actually a chair, even though all we see is a projection of the chair in one direction. Okay, so why graphics together with visualization, and what do we mean by that? So both graphics and visualization feed off each other. Visualization is one of the major applications of computer graphics, one of the major drivers also of computer graphics. Similarly, graphics plays an important role in the visualization pipeline. If you think of visualization as a pipeline, the last stage of that pipeline is essentially computer graphics, where we go from some representation of the world to an image. So we will see how both graphics and visualization can be studied as a pipeline, right? I will use this pipeline metaphor throughout the course. So this is one of the reasons that it makes sense to study both graphics and visualization together. Uh, on the ground, there is a lot of overlap. Um, uh, in terms of algorithms, in terms of techniques, and so on. So several algorithms for displaying volumes, for representing volumes, for efficient queries on these volumes were developed both within the graphics and visualization communities. So we will study them uniformly and see that they are applied to both graphics and visualization. Both graphics and visualization are about images. So the evaluation techniques, perception-based studies have a lot of commonality. In terms of the people who work on graphics and visualization, again, there is a lot of overlap. So this is historical. So these are maybe some of the reasons why it makes sense to study the two topics together. Right. So what is this course about? We are going to study, because this is a one semester course, we cannot cover everything under these two topics. So we are going to study essentially the fundamentals of graphics and visualization. This should be sufficient to take you, to help you kind of address any of the advanced topics and read research papers and so on. Now, what does it mean to look at the fundamentals? We will look at the foundational concepts and some of the key algorithms in both graphics and visualization. And I will give you a flavor of some of the applications in the lectures. Majority of the applications are what you will encounter in your course project. What I will not cover explicitly, but you will end up learning by doing things on your own, is the software associated with graphics and visualization, essentially OpenGL. And you will naturally be running these programs on graphics hardware, so you will get a sense of the graphics hardware as well. Right. So these will not be covered in lectures, but the idea is that you learn about them by getting your hands dirty and doing things in the assignments. For graphics, we will be focusing on how to model objects, how to represent and display the geometric objects. And in doing that, we will follow what is called the top-down approach, where in the first few classes, we will already be able to display an object without really understanding the details, right? So there are lots of details in order to understand how you go from an object to an image. So it's like driving a car, right? So all you need to know is the controls, the steering wheel, what happens when you press the brake and the clutch and so on. You don't need to know how the crankshaft works, how in the internal combustion engine works, or if it's a modern car, how the electric transmission works, right? But we will understand them later, right? In future lectures. So that's the approach that we will take. Just to be clear, especially for those who are outside of computer science, this is not a course on graphic design and so on. Not a course about packages. The idea, we will not be covering any packages, whether it is graphic design packages or visualization packages in the class. It will not be about graphics APIs. While we will use OpenGL, which is an API, the idea will be that we don't focus on a specific API in the lectures. The lectures will be about the foundations, right? This is clearly not about game design, so we won't be talking about those aspects as well. In terms of visualization, this is not about statistical graphics. So it's not about charts. It's not about how to efficiently choose how to visualize your kind of Excel style or columnar data, right? That's a different course in itself. We are not going to cover all that in this course. So in order to get a better feel for the course, I want to just run through the lecture topics. But before that, maybe I'll take a short 1-minute break and ask if there are any questions. We will come back to the administrative details to the end of the course. So if you have any questions about the technical topic that I have covered so far, then I can answer them now. Okay, I guess not. So let's jump into the outline of the course. What you will get out of the course after you complete the 3.5 months of lectures. After a quick introduction in this lecture and the next lecture, you hopefully will understand what is graphics. You should be able to explain what visualization is to someone who is another computer science person or someone from outside computer science. We will see some sample applications. As an introduction, we will understand the process of image formation. Another term that you could use for this is a synthetic camera. We will see what a synthetic camera is. We will also see the basic architecture of a graphics pipeline. There will be a lot that you can learn from the history of computer graphics. Often in my lecture slides and the notes that I share with you, there will be many slides which are grayed out. So these are meant as self-reading. I will not cover them during the lecture, but this should be self-contained and a lot of information available out there. So you can spend your time reading this on your own. In order to simultaneously cover the foundations as well as doing things, right, in order to learn, we will start from next week. We will start some assignments on OpenGL. These will be primarily assignments. There will be a small component of them which you can consider as a tutorial, but essentially you will learn by doing something, right, and not by sitting and listening to somebody speak. So we will have at least a couple of sessions where you will do some OpenGL assignments in order to get started. This is especially required if you have not done an undergraduate course on OpenGL or graphics. This will be in the second week of August, so next week essentially. Right. During this assignments, you will understand basics of OpenGL, what is its architecture, how do you set up a simple program to draw a polygonal object, an object in 3D, and so on. You will essentially be able to do some simple interaction with this object as well, right? And after that, we will, during this assignment, you will also understand what it means to, what it means when somebody says that I have a graphics pipeline and why they often talk about a programmable pipeline. So your graphics program will essentially be a C, C++ style program. Where the rendering is taken care of by something called a shader. And this shader is written in a shading language called GLSL, which is essentially like C, right? So very not too different from C. So you will essentially write a vertex shader and a fragment shader during these assignments and the tutorials. So one benefit of doing this upfront is that you can immediately jump into the programming assignments for the class as and when I cover uh, the relevant topics in my lectures. Okay, so what can you hope to see as output um, uh, from your first program, right? So you may not, if you have this model that we saw earlier, then you will be able to display a wire, what's called a wireframe representation of the sun. You will slowly incorporate what's called shading and uh, displaying of different planar primitives like triangles, right? And once you incorporate lights, you will be able to see a model which looks like this, which is more a smoother shaded. Moving on to the next set of lectures, we will understand what is called the graphics pipeline. The graphics pipeline takes you from your geometry that is used to represent the 3D world on the left, all the way to pixels on the right. Pixels are what constitute your images. The process by which your geometry, which is represented as a collection of vertices, uh, gets converted into pixels, is called the graphics pipeline. So the vertices go through this pipeline. They are processed initially. Um, they are transformed into different coordinate systems. They are projected, then the vertices are collected together into so-called primitives, triangles, edges, and so on. Then they are clipped so that you see only the part of the world that lies within your um, view volume, what's called the view volume. So essentially your field of view, right? If you have taken photographs, then you know what a field of view is. So far, we are until the clipping stage, we are talking about the 3D world, the 3D geometry. This has to be converted into images, essentially a raster image, a collection of pixels. This is done in the rasterization stage. And then there are some image processing methods that are applied called fragment processing that further improve the image that you're getting, that is getting displayed, right? And out comes from that stage the collection of pixels that are displayed on your monitor. So we will look at 3D graphics by going through the different stages of this pipeline, right? So, so essentially, we will study geometry, the basics of geometry, transformations, what is called homogeneous coordinates, the lighting, and what's called viewing, so camera transformations. Um, and after that, we will move on to some advanced rendering techniques where in order to generate high quality images, you need to incorporate things like a wallpaper, right? Uh, so these are called texture maps. So in order to introduce texture maps, I will talk about some buffers that are available in a graphics architecture. Then we will talk about this idea of texture mapping, or pasting wallpaper on top of your objects in order to get different types of texture. Let's say you want marble-like texture, or you want like a wood-like texture, right? Or you want to paint something like the sky, right? You cannot hope to model the entire sky with the clouds. So you create something like a wallpaper and try to paste that and try to make that look realistic. So for in the context of the sun representation, let's say that sun model was made out of some copper, right? And due to oxidization, this started showing these effects, right? So texture mapping is one way uh, to design and render such oxidization effects. If you want to make a mirror, so the mirror reflects everything in the 3D world, this can also be accomplished using this technique of texture mapping. So next we will study quickly some algorithms for the clipping and rasterization stages of the graphics pipeline. And then we will move on to visualization. So we will try to finish graphics within the first month and move into visualization algorithms. And we will come back to graphics as and when required during the remaining lectures. Um, so I will introduce visualization by talking initially about data representations. How do you go from data to images? What kinds of domains do we want to represent? How do we represent these domains, either as grids, like what you see here, or as a collection of points that you see within this grid structure, or a triangle mesh, right? A collection of triangles that represents your domain. As another option would be to just have, like I said, a collection of points. This is called scattered data. Then we will talk about interpolation techniques. This is called data reconstruction. We will look at different interpolation techniques. Some you are familiar with, some maybe you haven't studied explicitly. We will talk about some advanced interpolation techniques when you do not have a grid. We will talk about Voronoi diagrams here. And its dual, which is called the Delaunay triangulation. After this introduction to the data component of visualization, we will look at some classical visualization techniques. I mean, I'm going to spend maybe 10-15 minutes talking about these traditional techniques on function plots, glyphs, icons, and so on. But we will jump into something called isosurfaces, which helps visualize 3D data. We will look at algorithms for computing these isosurfaces. We will talk about efficiency of these algorithms and optimality criteria that they need to achieve. And once you go through these lectures, you should be able to process, let's say, a CT scan of a foot and generate different visualizations, such as what you see on the bottom here, in order to visualize the skeletal structure or the skin structure, or maybe the blood vessel structure, and so on. If you apply it to data from chemistry or data from the physical sciences, you should be able to look at atom structures as well. Like I said, we will study efficiency in these algorithms using different acceleration techniques. We will study what is called an output sensitive algorithm, or a variant of the marching cubes algorithm. Then we will move on to representing a volume by directly rendering it into an image, such as what you see on the top right here in the visualization of a scan of a single tooth. You can see that the entire volume of the tooth is represented here using transparency. So this technique that uses transparency and blending is called volume rendering, and is used both in graphics and visualization. So we will study the basics of ray casting, ray tracing, and then apply it to volume rendering. We will study other techniques, other algorithms as well for volume rendering. Next, we will move on to the visualization of flow, like velocity or force, and so on. We will study different techniques for this, simple techniques like glyphs to more sophisticated integration-based techniques like streamlines. And then we will move on to visualizing graphs and trees and hierarchical structures. So this is, by the way, the visualization of a streamline in a flow. And this is one of the visualizations we saw earlier of an interaction network, or actually this is co-voting network in the Congress, I think. So that more or less covers the majority of the topics that I will cover. There will be a few additional advanced topics that I will also cover depending on time. And I will The schedule is already available on the Teams under the class notebook, so you can take a look at that. We will have some uh, time during the later part of the course. I will try to incorporate some advanced topics during that, during essentially early November and so on, and maybe have some guest lectures. The material for the course. There are some books that are recommended, not necessary. But if you like to read from a book, then for graphics, I would recommend Angel. The 6th edition is appropriate because it still talks about shader-based OpenGL, and you should be able to relate that to what we cover in the class. This is still available in many bookstores and Amazon and so on. Earlier editions are also okay. Later editions are fine, but they do talk about the browser-based graphics called WebGL. So there will be some differences between that and what we cover in the class. Right. For OpenGL, I guess the go-to location is opengl.org. Besides that, all the algorithms that I cover will be from research papers. The primary venues for these are the IEEE WIS conference and the IEEE transactions on visualization and computer graphics. I will share links to these papers, or I will share the papers directly with you. In terms of the content related to the course, the course syllabus, the lecture slides will cover pretty much everything, and I will share this with you again on Teams. Look at the class notebook from time to time. And like I mentioned earlier, all the reading required for the courses will also be on the class notebook. Right. Additional resources that you need. You will need a workstation or a laptop which has a graphics card. I recommend that you work on your own laptop to the extent possible, because that gives you a lot of freedom to install whatever you need without worrying about disrupting the environment in a common machine. But having said that, the workstations in the Wells Fargo lab in the first floor are all equipped with a graphics card, so you should be able to use them. What you will need for the assignments and in order to learn the material in the class is OpenGL for the graphics rendering, and any windowing toolkit. FreeGlut is a bare bones windowing toolkit that allows you to create a window, to interact with it using your keyboard and mouse and so on. It's very light. It's lightweight as well, so easy to learn. The good thing about both OpenGL and FreeGlut is that they are available across all platforms. There is no restriction on what platform you choose, as long as you are able to manage it yourself. Right. For some aspects of the course, you will learn ParaView, which is a visualization tool and supports Python-based scripting. Optionally, you can look at what is called the Visualization Toolkit (VTK) and Qt, which is a windowing toolkit. And like I mentioned, the Teams will be the primary source of all information for you. The list of resources that could be useful are also kind of listed on the course webpage. Right. Okay, so I want to just wrap up this part of the introduction, more the technical content of the course, by talking about, so if you have seen the course webpage, you have seen these images, and you saw them also in my first slide. So I want to give credits to these images and talk about them a little bit. Some of you may have recognized them, especially if you have done graphics before. Um, does anyone want to venture a guess as to what they are? What they are called? The one on the top left. Maybe not. Okay, so the top one on the top left is a bunny. It's called the Stanford bunny. And the models of the teapot that you see in the middle and right are called the Utah teapot. So these are historically important. They um, uh, go back to the history of graphics. Um, so the teapot first, because it came chronologically earlier. So the Utah teapot, this is the original teapot made of porcelain and available in a museum. Um, so this was actually one of the teapots that kind of inspired Newell, who was a pioneer in graphics and geometric modeling, to actually generate a 3D representation of some model, right? So he took this teapot, he made measurements physically and represented this surface of this teapot using a quadric, a higher order surface. And he made that available in 1975 to the research community. So once he made that available, it was used extensively by different researchers to test their graphics algorithms. So they had a model to work with, so they could now display that model and test if their algorithms are able to render all the detailed geometry that's present in this teapot. Right. So this was hand modeled really. So and the original, if you are interested, is in the Boston Museum. That's the picture from the museum. The Stanford bunny is a little bit more recent. Like the name suggests, it comes from Stanford, from Mark Levoy and his group, Mark Levoy and Greg Turk, who were first working on a rain scanner. So you can think of this as the precursor to our Microsoft Kinect or any of the depth scanners that we have in the market now. So one of the first depth scanners was developed in 1994 by Mark Levoy's group. They were the pioneers in this area called computational photography and 3D scans. And the bunny was again available in some store, and they used that as a test for their scanner. So they took this toy, scanned it in because they were interested in it because it had a lot of detailed structure, and then made that scanned surface available to the research community. And to this date, this is often used to test different graphics and mesh processing algorithms and various rendering algorithms. You will often see them in research papers. The original of this is in Stanford. Of course, the models of both the teapot and the bunny are available now in many repositories. Right. So with due credits to them, I want to jump into the administrative details of the course. The prerequisites first. As you can imagine, this course needs a background from different disciplines, but this is what I think will be definitely required, right? So very strong programming skills. So I expect you to have done a lot of programming in your undergraduate days, and especially programming at the system level, right? So so setting up a program, compiling it, linking it, and working with makefiles, things like that should be kind of obvious to you, right? And you should have written at least medium-sized programs in your previous courses or maybe at work or something like that. Data structures and algorithms, at least an undergraduate level, data structures and algorithms is what I expect. We will be using several of these data structures in the class, and I will assume that you know them. In terms of the math background, essentially, again, undergraduate level linear algebra, because a lot of the transformations that we talk about are all represented using matrices and matrix multiplication and so on. So simple matrix algebra, I expect you to know. And geometry, essentially high school geometry, lines, planes, and so on. A previous experience with graphics will be useful, but not required. Undergraduate graphics will definitely be useful, but not required. But if you don't have an exposure, then you may have to put in additional effort in the beginning of the course to pick up OpenGL and start programming with that. Right. Okay, more administrative details. I will be the sole instructor. So if you have something very urgent, very important, you can send me a direct email. Or if you have something which is specific only to you, right, then you send me an email. But add the course number as a subject so that I know that it's about the graphics visualization course. There are two TAs for now, Dinesh and Nirmalya. I think both of them are in the team meet today. Their emails are also here. Again, emails only if you need something that's only specific, like specific to you, right? I recommend contacting via Teams and not via email, right? This makes it easy for you and for them and for me. For all general queries that is related to the entire course and maybe of use to the rest of the class, please post them on Teams. Right. I will give details about the team. You have already joined, many of you, but I'll give more details. The lecture time is fixed, 11 to 12:30. This first lecture, I will talk about the first lectures and the later lectures, but the lecture room is also fixed to 5 to. The course group will be used for everything. I cannot stress this enough. Everything related to the content, all updates, when things are due, everything will be posted on the on Teams. All assignments, projects, everything will be posted on Teams, and you will be expected to submit your work also on Teams. So here is the Teams code. You may want to write this down. I've also posted this on the intranet page. Some of you may have seen it already. Use that to join the team if you haven't done so already. The web page is essentially static snapshot of the course for viewing from outside IISc, right? It will not be updated much, but it does have some crucial content, so you can look at that also. Almost everything that's available on the course web page will be available on the Teams page. Right? Okay. So about the initial lectures and the later lectures. So this lecture obviously was online. So that I could record it, and I was not sure how many will attend, and the classroom is small. Now, this will be followed by a couple, like I said, some lab assignments next week. The TAs will inform you about the time for these assignments and the tutorials. They could be a combination of online and in class. Again, the TAs will let you know, right? But we will expect that you come prepared with your own computing device for these assignments, right? So please be prepared for that. We'll make recordings of at least of this lecture. I will make it available, and depending on the lab, whether it is online or not, we will try to see if that recording can also be made available. If not a recording, at least resources will be made available. Okay. The remaining lectures will be a combination. But before I talk about remaining lectures, I will say that for all the other lectures, there will be reading material, right? So all that will be made available on the class notebook. So I expect you to go through that reading material, some of them before the class, and some, as I mentioned, they could be after the class. Now, the remaining lectures would be a combination of lectures, traditional lectures. They could be discussions where I could ask you to read something beforehand or look at the lecture beforehand and then come for a discussion. It could be a discussion or it could be a quiz, right? Whatsoever. And that would be in 252. Right? But we will essentially meet in 252 from the next class onwards. Uh, what we will do there could be a combination of many things, like lectures or discussions and so on. Okay. So we will end with the evaluation. So this is tentative. There may be some minor changes, no major changes. The refresher assignments that are going to happen next week will carry a small weight where you have to essentially finish the tasks, right? There will be programming assignments, the primary evaluation component, 2 to 3 programming assignments. These will be based on the material that we have covered in the classes. They will be announced to you simultaneously as the lectures are going on so that you can start working on them. The grading for these assignments will be interactive. Essentially, you have to come and give a demo one by one. You will be graded for the work that you did. So you will have specific tasks in these programming assignments. You will get enough weightage or sufficient weightage for actually getting the work done. But there will be equal weightage, if approximately equal weightage, let me put it that way, for questions that you will be asked during the demo. So these questions could be on what you have done for the assignment. It could be on the foundations of the topic, right? And the grade that you get for that assignment will be a combination of both, right? The Q&A and the work that you submit. Please keep that in mind. We would have a quiz at some point of time in the course, right? That will carry a small weight. I just say 5 now, 5 to 10, let's say, right? There will be, this is sure, there will be a paper presentation or a visualization tool presentation. This will be a precursor to a course project that will be a significant component of this course. I'll expect you to work about 1.5 to 2 months on the course project. This will carry 30%. The paper presentation and the final project would be in team of 2. The final project would be would be one of many types. It could be an algorithmic exploration, a new algorithm for visualization or graphics, some theoretical studies there, or an implementation of an advanced algorithm, or an experimental study where you have an implementation already and you are designing data and testing and studying its behavior under different conditions, parameter studies and so on. Very systematic study though, or tool development. It could be one of many types. Your final project could be one of many types. I understand that you will be doing assignments in different courses. So here is the late submission policy. This is only for assignments, by the way. For every assignment, you will get at most 3 days late submission. But you can use this opportunity only once, right? So, so out of the three, let's say 3 assignments, you can submit at least one of the assignment 3 days late and without penalty. Um, Otherwise, the deadline is fixed and you will be expected to submit the assignment by that time. Okay, so use Teams for all queries, collaborations. You learn from your peers and understand the concepts. Have a lot of discussions. Um, Use this group for that purpose. But anything that you submit with your name, whether it's assignment, or quiz, or project, should be your own work. And any deviation from there, you have already heard from the DCC about the penalties that will be applied, right? The minimal penalty will be a 0 in the assignment. It could go to a grade reduction and escalate even further. So please be aware of this. This is the only time I will mention this, but it's there for you to see now in the slide. So with that, I end this discussion. And if you have questions, I can answer them.